welcome back. This is the review for number 6 in the spring of 2020, so make sure you're watching the right review for your summative. And first section that I see on our review is going to be the applications of exponentials. We did test this once before, but this is like a really important topic. So I want to try it again, and we'll see how you guys are working through the exponential. Formulas are going to be given to you though, so don't panic about that one. So like for instance here on this question, I'm going to give you this formula where it's a times 1, and then you have to decide whether it's positive or negative r to the t power. So in this question, because it says it's increasing 2% per year, that means we're going to use positive, and then 2% is 0.02. Remember, you can take the 2 and you can divide it by 100 on your calculator, or you can move the decimal point over 2 spaces. Let me move my microphone. All right, so they want to know if the population rate now is 626,000, so there's the A value, the initial value. When will it hit 1 million? All right, so because we don't know time, we're going to use our table to predict. So in Y1, we're going to have to type 626,000. And then in the parentheses, because it's increasing, we're going to do 1 plus 0.02 to the x power. And then we're going to watch the table to figure out when it approximately hits 1 million. And I think the answer is about 23 to 24 years. So somewhere in between here. So that's going to be your answer. You're going to say about 23 to 24 years. And here's what I will tell you as far as those of us who are really being successful on this section already, and we're really good at these. I'm going to offer some bonus score if you are willing to solve that equation through using logarithms and solve it with a more intentional answer. I'll talk more about this later at the end of the video when we get to that section of the test, but we'll come back if I remember to come back. Alright, so number 2, this time we're compounding interest at a various amount, so in this case quarterly. The formula is going to be given to you. It says A equals P times 1 plus, this time the rate is being divided by an n, number of times that you collect interest. And then up in the exponent, you're going to multiply your years by that n as well. So the n is really important to this question, and it comes from this. Compounded quarterly means that you are going to collect interest 4 times a year. So this guy right here becomes 4, and this guy right here becomes 4. So we start with $5,200, that's the principal. The rate, of course, is going to be this guy, but we're going to write this as 0.025. And then t should be given to you somewhere out there, number of years. Alright, so we are going to be on our home screen because we have everything we need. And this is money, so when you type, you're going to round to the nearest hundredth. So we have 5,200, parenthesis, 1 plus 2.5% is 0.025. You're dividing this by n, which is 12. And then up in your exponent, that 12 shows up again. And you're going to multiply it by 5 years. Okay, so that's a 60 if you want to simplify it, but either way, you're going to type all of this into the calculator. And in your home screen, you're going to get, let's see, $5,890.08. All right. Some of you got a little confused with the compounding formula and when to use what variable. Oh my gosh. Like me, like I got really confused, like right here, for instance. Oh my goodness, that was a 4. Okay, so that's a 20 up in the exponent. Hello. I think I was looking at the wrong question. I got a little confused. For instance, the next one says that you're compounding monthly. That's when I should have used a 12. My goodness, I apologize. All right, number 3. Oh, the birthday money question. It's back. So this is another one where if you choose to solve this algebraically, using our method we're going to talk about later, that I will give you some bonus score. So it doesn't tell you how much money, so you can invest any amount. For this value of P. So I always do $100. So I'm going to put $100 into the bank account. And then E is a number. Your base is E for continuous interest. This is the formula right here. Your R is given to you right here as 2%, so that means R is 0.02 as you write as a decimal. And then how long will it take? I don't know that, so we're going to multiply it by a mystery x. So you're going to use your table. Because you don't know time, you're going to get this typed into y1, and you're going to look for your money to triple. So for me, if I am, did I make that up? Yeah, triple. If I'm looking for my $100 to triple, I'm going to be looking for $300. And if I do that, I get about, and it takes me a while, right, 55 years. That's a really slow rate of growth, so it's going to take kind of a long time. We'll come back to those questions on how you can solve them to get a bonus score later on. I hope I remember. All right, the Warren and Judson question. You have to decide between two job offers. So Judson is going to give you a $35,000 salary and then a $900 annual raise. So this right here is the equation for Judson. So they're going to start you off with more money, but their raises are linear as opposed to exponential. So you're going to see a slower rate of growth. And then Warren has an exponential growth. They're going to start you out with less money, but they're going to raise exponentially. So when we look at the graph or we look at the table increase, we're going to see that even though Warren starts lower, it does end up giving you a percentage of a raise instead of a flat raise, and therefore it grows a lot faster. So you're going to figure out which job offer you're going to take, and this is where I can't really tell you how to write down the answer because it depends on your decision. Your decision is going to be based on time. So you have to decide. What I do first is I figure out when do the job offers differ. Like if it's so far into the future, like there's no way I'm still going to be working at this place, like that's going to be part of my answer. So here's what I do. I go to my calculator and I type those functions into y1 and y2. Calculator's a little slow today. And I try to figure out where the one job offer overtakes the other job offer. Of course, I have nothing typed in, so give me a minute. All right. So let's start with Judson being, where are we at? 900x plus 35,000. So flat raises grow linearly. They look like a line when I look at the graph, and that's not very exciting. But exponential growth questions end up growing very quickly, even though they might start with a lower number. So this one's starting at 25,000, but it's going to grow much faster. Okay, oops, I don't know what got weird there. I got an extra 7. There we go, to the x power. So first thing I'm going to show you is what the graph looks like. You don't have to do this step. We usually just go to our table. But when I go to my window, right now x represents time, and I don't care what happened 10 years before I graduated college and didn't start working. So I'm going to start at 0. And then as far as time goes, I'm going to go out into the future of this job. Maybe I'll go 15 years for now. Now the y's are going to be the amount of money you're making. And the lowest job offer I had was like, what, $25,000? So I'm going to start my y's at $20,000. And then my maximum salary, like, I don't know. A girl can dream, right? Let's go to $100,000. And let's graph this. So that first blue line, that was Judson. And yes, it does start with more money, but it's growing very slowly. And then Warren starts with less money, but eventually it grows much quicker. So you can actually find this point of intersection using your calculator by choosing the intersect option right here, number 5. And then just hit enter, enter, enter 3 times. And right here it tells you exactly not exactly, but close to exactly 7.6 years into the future is when the other job offer will overtake, and you'll make more money at Warren versus Judson. Now, for everybody else, if you just went to the table and you kind of scrolled down and you watched for when the red one all of a sudden was more money than the blue one, that happens right there. So at about 8 years, we would just say about 8 years into the future. So I actually answered this last question first. So I'm just going to say about 8 years. And I wouldn't mind if that was part of your answer up here. So which job offer am I going to take? So maybe your answer here will say something like, I don't intend to stay at this job for more than a couple years. It's a stepping stone job for me. so therefore I'm going to stick with jettison because they're going to pay me more money. Or if you specifically say something like, you know, I want to stay at this job forever, I really want to stay with this company farther than 8 years into the future, so I'm going to go with Warren because after 8 years of work, I'm going to be making substantially more money from that point on. So your answer is going to vary, and that's why I can't give you the answer to this one. Just make sure that you mention time. So I'm just going to write that as a note. Be sure to mention time. I've had people explain this question differently. They took a different approach and they said, well, I need as much money as possible like right now. I need to pay for things. I need to pay for my college loans. So I'm going to go with jettison because it's paying me more money right now for the next few years, and then I'll reevaluate, you know, maybe later on. I think that's a great answer, okay? I can't answer this for you is the problem. Okay, this next part, this is a retake, and we're going to need to do better on this one, guys. So one of the issues we saw was maybe you didn't understand the formula. So log form is where you have the abbreviation for log, right? And then it's got some base number down here. And then inside of the logarithm, there was something, which I'm just going to call the number. And your log formula equals an answer. Well, that's great, except when you had to rewrite it. So the base is still going to be the base over here. It's going to hold up the exponent, and then the number and answer switch, right? So the answer becomes the exponent, and then what was in the logarithm becomes your answer. So what I do on these questions is I figure out who the base is, and then I just remember that these guys are just going to flip-flop in order in which they appear. Okay, so I look at number 6a and I say, boom, there's your base, y. So your base is still a y. And then I think about these numbers switching. So the 2 now becomes my exponent. And then what was in the logarithm, the x, becomes my answer. I think if you guys start approaching it that way, you'll have better luck. I did not give you the formula on that one, and that is why it got a little tricky for some of you. All right, so again, on number 7, if you can identify who the base is, you'll be good. So like, boom, right there, there's the base. So you're going to have to write log, and then he's going to have his same base of y. And then remember, these numbers are just going to flip-flop. So the next thing I write down should be a 26. So I like when you write it inside of the logarithm, but whatever, you don't need the parentheses. And then the 4 becomes my answer. So that was the first challenge that some of you encountered on the last test, is you didn't have that formula down. And then the next challenge was these guys where you can use your calculator. I'll show you a little trick in a minute. But I want to know what this answer is. All of these can be done in your head. So you say things like, okay, who's my base again? My base here is an 8. So you say 8 raised to what power would give you an 8? And the answer is 1. So whatever that power is, that's the answer to this question. Oh boy, this one might be a thinker, huh? So your base is a 4. So you say like 4 raised to what power gives me a 4096. Now this one I might need to use my chart or maybe a calculator, but the number can't be that big, guys, because 4096, like, it's not a crazy number. And exponents get really big really fast. We saw that on that application question. I don't have a key, so I'm trying to type some things in my calculator. Looks like it's the 6th power. 4 to the 6th power is 4096. Now, be careful on this one. Some of you got this property a little confused. 5 to what power would give you a 1? Well, that's a power of exponent. Property of an exponent. Anything to the 0 power would be equal to a 1. Now, this one gets a little tricky, too. This is a base of 8. So 8 to what power gives you a 1 over 64? Well, the fact that you need to flip it to a fraction means that you need a negative. And then to change an 8 to a 64, you're going to need a 2. So be careful about that guy, all right? So yeah, that's a repeated section. Please do your best, and let's get some 5s on that section. This is the new stuff. So we're going to be solving equations, And I'm going to give you some questions where you can solve them using the common bases or the baby bases in some cases. Some you can't. And I like the baby base method. I think it's nice. So I'm going to look for it. If it's there, I'm going to use it. This one right here is definitely a baby base question. So remember that chart. You can use this on your test. And I did make some extra copies. I noticed 7 and 343 are in the same row. They're in the row of 7. So I'm going to keep 7 as a 7. But I'm going to change 343 to 7 to the third power. I don't know why I wrote parentheses. I don't need them. All right, so this is still 7 to the, I can't read it, 2x minus 5. Okay, so now that you have the bases matching, if you had exponents here, you'd have to combine them, but we don't have that. So here's what I'm going to set up. These powers have to match. So 2x minus 5 has to equal a 3. And then I can solve this equation with just a few algebra steps. I'm going to add 5 to both sides. I got 2x equals 8. So x equals 4. Ooh, hello, that's a 2. I really like the baby base method. I think it's nice. It doesn't involve a whole lot of typing, especially if you can identify that baby base pretty quickly. However, every question on this section, even the baby base ones, could be solved using logarithms. The next couple must be solved using logarithms because you can no longer find a common base. For instance, here you have an e, which is a really funky irrational number, and then you have a 10. So no, I don't think those have anything in common. So what you're going to do here is you're going to apply the common log, or you can apply the natural log to both sides of the equation once the exponential piece is isolated, once the base is isolated. So here it gets, it confuses kids a little because they're like, oh, I have an e and a 10. Which one should I use? Normally it doesn't matter. Actually, always it doesn't matter, but sometimes it'll make your life easier. If you notice your base of the exponential piece has an e, you should use a natural logarithm. So I'm going to apply a natural logarithm to both sides of the equation. What happens right here is that you have some cancellation. The natural log and e will cancel, but on this side, you need to type it. So, natural log and e cancel, and then the x minus 7 drops down. And then the natural log of 10, I think I already have this one solved up. Let's see. The natural log of 10 is 2.303, it looks like. And then our final step to solve the equation would be to add 7 to both sides. So 9.303. And you shouldn't be getting real pretty answers on these next few. They should be kind of gross. All right, when I look at number 11, we are going to apply a logarithm, but not yet. I need to isolate first. So, what I mean by that is this 5 to the x power has to be isolated, and you can trust your instincts here, guys. You're going to add 7 to both sides, and maybe you're not sure why, you just feel like you need to, and you do. And then we're going to have one more step of isolation. We're going to divide both sides by a 4. This 4 is being multiplied right... Oh, hello. Got a little forward thinking there. Divide by 4. This problem has a multiplier of 4 in front, so we're going to divide it over. So now my question says 5 to the x power equals 8. So now you can apply any logarithm you want. Some of you really like the common log, even though you know my feelings about this, but whatever. You can do that. We can apply the common log to both sides of the equation. And unfortunately on this question, nothing cancels. So what happens is the reason you applied the logarithm is so you could bring that exponent down in front. And now it's being multiplied by the common log of 5, which is just some gross number on our calculator. And it equals the common log of 8, which again is also some gross number on your calculator. So if you're trying to solve for x, you would simply divide the common log of 5 over to the other side. Now this is a typing question. This has to be typed. And then close your parentheses after each logarithm so you don't have a mistype. And I think you end up with, let's see, 1.292. There we go. So I want to go back to that application question real fast. Let's do the birthday one, for instance. This guy. So this birthday question where you wanted to know where it tripled, right? So we had $100 at 2%. I'm going to show you what it looks like to solve that without using your table. So we wanted our money to equal 300. This is for like an extra bonus score, okay? And we invested $100, and then e to the 0.02 times x power. This is why we always tell you it doesn't matter what you invest, because your first step in solving this equation would be to isolate. You divide by 100 on both sides, and you're going to get 3 equals e to the 0.02x. This is why Mrs. Meyer and I always tell you it doesn't matter. If you put $10 here and did $30 here and you divide them, you're still going to get this factor of 3 every single time. So we really mean it when we say it doesn't matter. Now, I'm going to apply the natural log to both sides. And let's see what happens. So this I need to type on my calculator. This, the natural log and the e cancel. Those are inverse logarithm and exponential pieces to each other. Oh boy, guys, I don't know what that is. Natural log of 3. Let me type. That is 1.099 roughly when you round. And then remember these cancel, so you got 0.02x, which will just drop down. And then you're going to divide both sides by 0.02. Divide by both sides by 0.02. And you get x equals 54.93. So if you can solve those equations, and I'll put a big note on the board, if you can solve those table equations using algebraic methods to the nearest hundredth accurately, I will give you a bonus score. And not just in my heart, but literally in the grade book. Okay? So what a deal, what a deal. Alright. Let's continue on. My favorite, solving logarithmic equations. So you solve log equations by exponentiating the equation. And exponentiating is where you use exponent property and you shove everything up to the exponent. So you can choose any base you want, and you want it to match your logarithm. So like 12a, super easy. This has a base of 3. So this problem, the 3 is now your base, and you shove everything up into the exponent. The reason you did that is because right here and right here, you're going to get some cancellation, I should say. Cancel. So this turns out to be like the world's easiest linear equation. 9x minus 4 equals 3x plus 20. And then we just solve. So I'm going to subtract 3x from both sides. While I'm at it, I'm going to go ahead and add the 4. What do we have here? 6x equals 24. So x equals 4. They're not all that easy though, because you got to think about like what you're actually doing, and this is where the concept errors occur. 13a, first of all, it's not isolated, so you need to isolate first. So I'm going to subtract the 4. So the logarithm component is what I'm trying to isolate. So you have log base 6 of x minus 1, and it equals 2. So now we're going to exponentiate with the base that matches the logarithm's base. So I'm going to shove a 6 underneath both sides of this equation. And I don't usually take the time to do this, but I think now is a good time to look at this. What you guys have now is 6, and then up in his exponent is log base 6 of x minus 1. And it equals 6 squared. So the reason this works out mathematically is because right here, you're going to see that these cancel. And then the x minus 1 will just drop down. And then 6 squared, not 6 times 2, but 6 squared, that is a 36. So all of a sudden this became a really easy question, as long as I knew to exponentiate both sides. Alright, 14, again, you need to isolate first. You got 2 steps of isolation. So I'm thinking we need to add a 5. And then we're still not done, because then we're going to have to get rid of that 4. So 4 is being multiplied right now, so let's divide by 4 on both sides. And finally, we have the natural log of x minus 2 equals 3. So now we're going to exponentiate. And then you have to remind yourself, and if you forgot, you can take a look at your calculator. The common base, or the base of a natural logarithm is the number e. So e gets shoved underneath both sides of the equation. And again, I don't usually take time to write this, but I'm going to this time. The problem now says e to the natural log of x minus 2 equals e to the third power. These are all things that you could type on your calculator when it comes to e, because you have that wonderful button above the natural log. Again, you're going to see some cancellation here. And that means the x minus 2 drops down. And then e to the third power is something I need to type on my calculator. It's like 20.086. I'm looking at my key right now. And then final step is we're going to add 2. So, final answer, 22.086. Again, these don't always come out pretty, and that's okay. Sometimes they're really weird answers, especially if you have a base like e, an irrational number. Okay, that is your test. I'm really hoping for some good scores. This is the end of your quarter, and I'm going to be sending home midterms, and I want to report back with good news. All right, good luck, everybody.